Welcome to the third video on determining the reactions of indeterminate torsion bars. In this video, we'll actually go through and set up the equations required to solve for our reactions at A and B, and we will actually determine them. Now that we've determined the value of J, the polar moment of inertia, we can combine our equations for the rate of twist, which we said was the length times the maximum shear strain, divided by the outer radius. We can combine that with an equation for the shear strain. The shear strain is going to be equal to the shear stress divided by the shear modulus. So slapping these together, we're going to be able to obtain, I'll write this in green, that our twist is going to be equal to the length of the section times the torsion in that section divided by the polar moment of inertia, and also divided by the shear modulus. Now, this is the end, right? So we've got the rotation that we experienced from A to C, there is no D, is equal to the rotation from C to B. So we can write that the rotation from A to C will be equal to 125 millimeters. The length times the torque from A to C, which will be constant. Of course, if we apply the torque at A and there's nothing going on between A and C, then, well, it's going to have a constant torque in the section from A to C. Then at C it's going to change, but let's just write that as that, and divide by the polar moment of inertia, which we said for this, from the section from A to C, was 15,708 millimeters to the fourth. And then G. We won't worry about the shear modulus because it's going to be the same in both cases. We're saying that this has to be equal and opposite. So it's going to be equal to the rotation from C to B, which will be this 125 millimeters rather than this 125 millimeters. So it's 125 millimeters for both of them, but this one is this length, whereas this one right here in the AC is this one. Times the torsion from C to B. We divide that by, this time the polar moment of inertia is different because we said this was hollow, and so this is going to be only 11,936.5 millimeters to the fourth. That's also divided by the shear modulus. That's equal to the twist from C to B. So we can rearrange these, and that will give us our relationship between, I guess, the ratio between TAC and TCB. Now, once we've got those, we can plug them into our other equation that is, I guess, a little bit easier. It's going to be that the torque in AC, or the moment in AC, about the x direction, plus the torque in CB has to be equal to 120 kilonewton millimeters. So rearranging these, we obtain, combining these two equations, we obtain this. And then working our way through it, we will, simplifying this all out. And that one equals from the rotation from C to B. Simplifying all this out, we can, it won't be equal to the twist at AC if we remove these values that are the same, but we can do it. We can certainly take out G. If we multiply both sides by our shear modulus, we will end up with the same true statement, I guess not the same true statement, but it will no longer be setting the twist equal to each other. It will be setting the twist times the shear modulus equal to each other, which is a perfectly fine thing to do. So let's do that. Let's leave the lengths in, but remove the shear modulus, because I didn't even give a value for that, and we don't need one. And it will almost always be either the same or able to be folded into with J. So we'll end up with 0.0079577 times the torque from A to C, and that's going to be equal to 1.25665 kilonewtons per millimeter cubed. That's also being present here. We're getting millimeters cubed down there, minus 0.01047, and that's times the torque from A to C, and we'll divide that by millimeters cubed. Sorry, this should be millimeters squared right there. These are millimeters cubed, because these torques are going to be using moment units. Moment units are, of course, force times length. So we can simplify this further. Now we've got just this one equation with the torque from A to C, and we're going to obtain that from A to C, the torque is going to be 1.25665 divided by 0.01843. Sorry, that's kilonewtons millimeters. That's going to end up giving us 68. That's how you draw 8. 0.2 kilonewton millimeters, which passes the smell test for me. Right, this portion right here from A to C is a solid bar, so it should be picking up more torsion because it's going to take more torsion to twist it to whatever extent we're twisting it at C than C to B will. So we're going to be looking at more than half of 120 kilonewton millimeters, and this is just a little bit more than half, which is 60. I really hope you knew that off the top of your head. So now, getting to the torsion from C to B is pretty easy. It's going to be 120 kilonewton millimeters minus 68.2 kilonewton. Yeah, that's how ends work. Millimeters, which is 51.8 kilonewtons millimeters. Do note, of course, that the direction of these torques will be the opposite. The internal torsion will be opposite from A to C as it will be from C to B, but it's math-wise much easier to do this like this. Let's also check, plug these values back in to obtain the torque, or to obtain the twist from these torques and the shear modulus and the polar moment.